Yo, what's up, super peeps? We're going to keep going here with chapter 8 notes. Okay, so we're going to take some of the Lewis structure stuff that we've been talking about, and we're going to start applying it and looking specifically at the bonds, a little bit about strength, all right, and then we're going to take a little bit closer look at those bonds. So we're going to start with strength and length of these covalent bonds. Now, there's a general statement that we can use. In general, as the number of bonds between two atoms increases, the bond, grows shorter and stronger. Now, to me, this just kind of makes sense, all right? So if we compare these three bonds, right? We got a carbon single bond, a carbon double bond, and a carbon triple bond. So this is only sharing one pair of electrons. This is sharing two pairs of electrons. This is sharing three pairs of electrons. Just by knowing that, which do you think is the strongest bond? All right, well, probably this triple bond is the strongest bond. Right now, if this bond is the strongest, which means this force of attraction is the greatest, what's going to happen to the length of this bond compared to these? Well, this one's going to be shorter than this one, and this one is going to be shorter than this one. And that's exactly what we see. Now, we need to talk a little bit about this bond strength. And then I'll come back and actually give you some numbers. So if you remember, bond enthalpy is the enthalpy change remember, enthalpy change is delta H for the breaking of a particular bond in 1 mole of a gaseous substance. Okay, so what this is really just giving us the strength of our bond. So it indicates the strength of the bond. So what I want to do is I want to come back up here and I want to give you some numbers just so you can actually see what's happening as we go down this list. All right, so let's do, length and enthalpy, which is our strength. So if we look at the single bond, the carbon-carbon single bond is 1.54 angstroms. If we go to the double bond, it's 1.34 angstroms. Okay, they're getting closer together. And then finally, if we go down to this triple bond, it's 1.20 angstroms, even closer. Right now, what's happening to the strength of this bond? Okay, well, how much energy does it take to break that bond? It takes 348 kilojoules per mole. How much energy would it take to break a double bond between two carbon atoms? It's quite a bit more, 614 kilojoules per mole. Triple bond, 839 kilojoules per mole. Right, so you can see that this strength is getting stronger and stronger and stronger And as that strength of attraction is getting stronger and stronger and stronger, the atoms are getting closer and closer together. Right? And this is true in pretty much everything that we see when we compare these single, double, and triple bonds. Okay. Now, we can actually use these enthalpies to calculate delta H's of reactions. So we can use these bond enthalpies to actually calculate delta H's. Right, now, I actually copied this right out of the textbook. Right, so these are some different bond enthalpies. If we just take a quick look at here. So these are all in kilojoules per mole, but it gives you a whole bunch of different bonds. Right, so here's the carbon-carbon bond that we were just talking about. It's the single bond. Actually, they're listed down here. Here's your double bond. Right, here's your triple bond. All right, but it gives you all these bond enthalpies. We can use these bond enthalpies to actually calculate some delta H's. Now, they're not perfect, but they get you really, really close. Okay. So we can use bond enthalpies to estimate the delta H of reaction. Now, in reality, what we're going to be doing is using a form of Hess's law. So we can think of a reaction as two parts. The first part of the reaction is we're breaking old bonds. So in the reactants, we got to break the old bonds. That's the first step. All right, now to break bonds, that's an endothermic process. Our second step is to make new bonds. And whenever we make bonds, this is going to be exothermic. So if we can put these two steps together, we should be able to get the overall reaction, delta H of reaction. So if we put these together, we can estimate the delta H of the reaction. Now we're going to use this formula. Our delta H of reaction is equal to the sum of bond enthalpies of broken bonds minus the sum of the bond enthalpies of bonds formed. It's broken bonds minus formed bonds. All right. Let's go ahead and try it. And we're going to start with a simple one. Using bond enthalpies, calculate the delta H of reaction for the following. CH4 plus Cl2 goes to CH3Cl plus HCl. Okay, so this is an organic reaction, but right, so what we're going to do is we're going to estimate the delta H of reaction by looking at the breaking and the making of new bonds. All right, so CH4 is methane. Okay, we got diatomic chlorine. And one of the hydrogens comes off and a chlorine is replaced on there. And then we have a bond here. Okay, so we can look at the bonds formed and bonds broken. So now, okay, if we compare the carbon atom or the carbon molecule to this carbon molecule, okay, we're breaking one CH bond. Okay, so one of these CH bonds is being broken. We have to break this bond. Now on the other side, we're forming this bond. And we're forming this bond. Right, so we're breaking one bond here, we're breaking one bond here, we're forming one bond here, and we're forming one bond here. Now it's important to look at the coefficients, and I made this one simple because it's balanced with just ones, right? So let's go ahead and calculate this. So the delta H of our reaction is going to equal the sum of our broken bonds minus the sum of our formed bonds. So now we need to know what the enthalpy of this bond is, all right? And we can go right to this. Okay, here it is, 413 kilojoules. Okay. Plus we have to break this chlorine bond. And here it is, it's 242 kilojoules. Minus, now we're forming an SECl bond, and if we look that up, it's 328 kilojoules. And we're forming an H and a Cl bond, which is 431 kilojoules. And when we do that math, we get negative 104 kilojoules. Now, what does that negative sign tell us? It tells us that it's exothermic. And that is actually pretty close to the real delta H of that reaction. All right, so that was a simple one. Let's try a little bit harder one. So, using bond enthalpies, estimate the delta H of reaction for the combustion of ethane, which is C2H6. Well, in this problem, the first thing we actually have to do is we have to write the combustion equation. So we're going to take C2H6 and we're going to react it with diatomic oxygen, and these are all gases. And it produces carbon dioxide gas and water vapor. And if we balance this, let's see, this will be a 2, this is a 7, this is a 4, and then this is a 6. Okay. Now, we're going to be breaking old bonds and we're going to be making new bonds. So I like to draw out either my Lewis structures or my structural formulas. So this is ethane. Oxygen has a double bond. Carbon dioxide has a double bond. And then our oxygen has single bonds. Okay. Now, you have to figure out how many bonds we're breaking. Right? Now, we're breaking a lot of bonds because none of this is on this side over here. So none of this methane. So every single one of these bonds is breaking. So we're breaking 12 carbon-hydrogen bonds, and we're why 12? Sorry, I should back up. There's 1, 2, 3, 4, 5, 6 hydrogen bonds here, but because of the coefficient, there are actually 12 hydrogen bonds that are being broken in this equation. There's 1 carbon-carbon single bond, but I have 2 of them, so I'm gonna break 2 carbon-carbon bonds. I'm going to break 7 oxygen double bonds. Okay, and we're going to do the same thing. What are we going to make over here? Well, over here, we're going to make, okay, so there are 2 double bonds here times 4. So this is 8 doubles. So we're going to make 8 carbon double bonds. Okay, and we're going to make 1, 2 times 6. We're going to make 12 oxygen-hydrogen bonds. So now that we know all that, now we can actually get it into the equation. So our delta H of reaction is equal to the sum of our bonds broken minus the sum of our bonds formed. Now we can already take a guess if this is going to be endo or exothermic. Okay, so we're burning this. Okay, so this should be exothermic. So our answer should be negative. All right, so let's go ahead and put in our numbers. All right, so let's start with this guy. All right, so we have 2 different ones that are happening here. We have 12 CH bonds. Okay, and if we look up that enthalpy of CH, it's 413 kilojoules plus 2 carbon single bonds, and that would be 348 kilojoules plus 7 oxygen double bonds, and that's 495 kilojoules minus, now we're going to form bonds. So we have 8 carbon oxygen bonds. 8 times 799 plus 12 oxygen hydrogen bonds, and that's 463 And we add all that together and add that together and subtract, we get negative 2,831 kilojoules. Okay, and it is definitely very exothermic. Okay, we get a big number. So lots and lots of heat is released. Right, so this is just another way of calculating that delta H. And it's using these bond enthalpies. Now, on the test, you'll have something like this, or you'll have a list of those bond enthalpies if I need you to do those calculations. Okay. All right, good. So let's get a little bit more in detail with our single, double, and triple bonds. Okay. And I want to talk about sigma bonds first. Right, it's the Greek letter sigma. All right, it's an O with this curly Q. So we're going to talk about sigma bonds. So we're talking about covalent bonds again. So a covalent bond is formed by the sharing of electrons. Now, in a sigma bond, the electron pair is located along the internuclear axis between the two atoms that share the electron. Okay, let's see if we can define this a little bit better. In a sigma bond, electrons are shared in an area of space centered on a line running between the two nuclei. And I want to draw some pictures. So let's say that we have, let's look at diatomic hydrogen. Right, so each one of these has an s orbital. Right? That's where their valence electron is in the 1s orbital. So if you remember, an s orbital is just this sphere-shaped area of space. Okay, so this is my s orbital. I got this cloud, and this is my s orbital. So these are spherical. Now, when these come together, these orbitals overlap. Can we get this area of space right here where the two electrons are shared? So we have this area of space in between them where the orbitals overlap and the two electrons are shared in this area. Now, this is a sigma bond because these two electrons are centered on the internuclear axis. that internuclear axis. So if this is the nucleus over here, this is the nucleus over here. If we draw a line between the nuclei, our two electrons are centered on that internuclear axis. Okay, so this right here is our internuclear axis. Which makes it a sigma bond. If it's on the internuclear axis, it's a sigma bond. All right, so whenever s orbitals overlap, we get sigma bonds. There are other ways to get sigma bonds. We can overlap an s and a p orbital, and it'll be a sigma bond. So, for example, let's say we have, I don't know, HF. So, hydrogen's valence electron is in that 1s orbital. Okay, so there's the nucleus. All right, this would be my 1s orbital, and I'm just going to use a circle. Is that okay? We know that it's an area of space. All right, so this is hydrogen. And then in fluorine, the valence electron that's free is the 2pz, okay, 2pz orbital. Now, if you remember, a p orbital looks like a dumbbell centered on that nucleus. Now, these are going to overlap. Okay, so when HF comes together, they're going to share those valence electrons. We end up with something like this. So here's my hydrogen. Here's my fluorine. Right? And when we actually look at this, it looks something like this. Okay, so here's the nucleus of this. We end up getting an orbital something like this. It goes 1. And my 2 electrons are shared in this area right here. Now, this is a sigma bond. Why? Because these 2 electrons are found right on the internuclear axis. So if I draw a line from the 2 nuclei, oops, okay, they are on that internuclear axis. So this would be a sigma bond. We can form sigma bonds between 2 p orbitals. Okay, so let's say we have diatomic fluorine. Okay, their 2pz orbitals will overlap. Okay, so this is that's one of my F's. Here's my other. Okay, these are going to overlap. And we end up getting something like this. And this is where the 2 electrons are found in between them. Right, this is my orbital overlap. So this is going to overlap this guy. Right, now, this is another example of a sigma bond. Because if we draw this internuclear axis, so here's my nucleus over here, here it is here. If we draw a dotted line, there's my internuclear axis. Those electrons are centered on that internuclear axis. So this again is a sigma bond. Now, we haven't talked about them yet, but we're getting there. A sigma bond can happen between hybrid orbitals also. So we don't need to know what a hybrid orbital is yet, but just realize that these sigma bonds happen with these hybrid orbitals. Okay? And again, the electrons will just be centered on that internuclear axis. Now, there's one other type of bond that we're going to talk about, and that's called a pi bond. So pi bonds are a covalent bond made from the sideways overlap of two p orbitals. The electron density of the pi bond lies outside the internuclear axis. So my electrons are not on the internuclear axis for a pi bond. So in a pi bond, parallel p orbitals overlap and occupy a space above and below the internuclear axis. All right, this is a little tricky to draw, but let's try it. So when we have a pi bond, when two p orbitals overlap, when they're parallel. Right, so first of all, let's just go back and make sure you understand. Right, in this case, when they overlapped, okay, they overlapped one end to end each other. Now what we're going to do is they're going to be parallel. Okay, so here's one p, here's the other p. Instead of going end to end, now these are going to overlap here and here. So what we get is something like this. Let me try. Okay, so here's 1p. And here's the other. So the orbital overlap is happening up here, and it's happening down here. So this is my overlap. Okay. Now, here's my nuclei. It's happening above, and it's happening below. Okay, so if these are the nuclei, we have an area of space up here where electrons are being shared, and an area of space down here where electrons are being shared. Okay, so I get electrons in here and electrons in here. If we drew the internuclear axis, the electrons are not on those internuclear axes. They're above and they're below. That's what makes this a pi bond. Okay, so my electrons are in an area of space above and below the internuclear axis. So this makes it a pi bond. Now, sigma bonds are stronger than pi bonds. Okay, so our sigma bonds are much stronger than our pi bonds, right? But I don't know if I can show this to you or not. I'm going to try. Okay, so see if I can zoom out here at all. Okay, so these would be s orbitals. Okay, now remember the nuclei are right smack dab in the middle there. All right, so when these two overlap, okay, the electrons would be shared here in the middle. It would be right on this internuclear axis. Okay, that would be a sigma bond. Okay, there's an S. This would be a P. Oops, can you see it? There it is. That would be a P, and if these overlap, okay, again, my nucleus is here, my nucleus is here. This would be on the internuclear axis, okay, so that overlap, that would be a sigma bond. Two P's. It would look something like that. And again, nucleus is here, nucleus. No, that's not what I want to show you. This would be a p orbital, sorry. Sorry. Okay, so here's my nucleus. Right now, and it's hard to see, but here would be my overlap. Right, so here are my nuclei. This is right on the axis. All right, so this right here, okay, would be a sigma bond. Now, what happens with a pi bond? Well, the pi bond, they're not end to end. Now they're like this. Okay, and these p orbitals overlap, and they're going to overlap here, and they're going to overlap here. So here's my internuclear axis. Now my electrons are off of it. So my electrons would be up here, and my electrons would be down here. Right? So they would be off my internuclear axis. So this would be a pi bond. Now, let's write this, and then we'll come back to this. So a sigma bond no, that's not that way. Let's do it this way. Single bonds are usually sigma bonds. double bonds are usually 1 sigma and 1 pi bond. Triple bonds are usually 1 sigma and 2 pi bonds. Now, I don't think this is going to show up. Is it? No, it's not going to show up. It's too big. Of course. What a pain in the butt this is. So if you remember, how our P's are set up, okay, they're like this, and then this would be coming out. So this is my Px, Py, and my Pz. Okay, so if you remember, okay, my Px, Py, Pz. All right, now, in a triple bond, 2 of the p orbitals overlap with another one. So you got to think about it this way. Remember, for a pi bond to form, okay, we have to have p orbitals that overlap, right, that are parallel, right? So if this is another p orbital coming in, okay, it's got to be parallel. So we could have one here, overlap with this one, okay, and we can have one overlap here and here. Okay. So those would be my 2 p's. My S would be this. It would go with this one, right? And I know it's hard to see because I don't have a lot of space, and I'm sorry about that. Right, so this would be in my triple bond. Okay, this would be my S, or my sigma bond. And then I would have 2, okay, orbital overlap there, and orbital overlap here. That would be my triple. Now, in a double bond, you have 1 pi bond. Okay, so maybe this overlap with these 2, and 1 sigma. Okay, and 1 sigma. Now, why can't you have 3 pi bonds between 2 atoms? Well, they're never going to all 3 of the p orbitals can never be lined up. They cannot be lined up parallel with each other. So, okay, they can be parallel here and here, right? But this will never be parallel to these, all right? So you can only have 2 pi bonds. All right, so I hope this helps a little bit. And that's where we're going to stop for today. Right, and we will pick up with molecular shapes tomorrow and VSEPR. All right, so have a good one, and we will see you soon.